Hello everyone, good morning, good afternoon, wherever you are. Thank you for joining me on this session on how to test and monitor your distributed applications in the cloud. The goal of this talk is to help you get from this point where you have a lot of trouble monitoring and testing your distributed applications to the point where you are all working together and all in control of your applications. My name is Henry Been and I am a developer and architect from the Netherlands. And I've been working for a while now with cloud applications and more recently with distributed applications, and it is my pleasure to share with you what I have learned. If you have any questions during this talk or after this talk, feel free to reach out to me on Twitter, LinkedIn, or even on email if you fancy that. Now, this talk is not about self-promotion, but I very quickly wanted to call your attention to a book that I've written together with Mike van der Graag, also from the Netherlands. It is a book about implementing Azure DevOps solutions, both about Azure DevOps and Azure itself. And it is a book designed to take you all the way from source control through continuous integration, continuous deployment, infrastructure as code, databases, application monitoring to a DevOps way of working. And normally when you're at a conference, you will get like 2 or 3 books to give away. But since we're doing this virtually, I have received a discount code from my publisher that I'm able to share with you. So if you're interested in this book, you can now get a 20% discount using the promotion code on the screen. Alright, enough about this. I want to start this talk with a little bit of a story. I think it's been well over 1.5 years, maybe even 2 years ago, when I started building a distributed system. We had a brainstorm with 2 architects about a system that we were thinking that might help us in a very specific situation. And as a developer, I started building a transactional engine at the core of a solution, another component that bootstrapped some data, just another component that initiated transactions on that engine, and a number of downstream execution agents. Something like this. A number of components working together, all disconnected, using functions, HTTPS calls, and service bus messages. Very much like what you see in a lot of demos nowadays. And when building this application, I noticed that I could build a very good proof of concept for the application in only 3 weeks. So with that respect, functions, service bus, logic apps, all these fast developed solutions, they really deliver what they promise. You can really quickly build a solution very fast. However, after this proof of concept, it took us another 3 months to build the thing, and before we had our first customer onboarded on this solution. And after hitting production, it took a total of 6 FTE to run and further develop this application for 1.5 years, and add extensions and keep the thing running while we're developing it. There is a quote that I want to call your attention to at this point, and it's called, good decisions come from experience, and experience comes from making bad decisions. It's a quote by Mark Twain, and I think you see it a lot on the internet. But there's also a second part to this quote, that this is life, so never regret. Learn from your mistakes and go ahead. And that's what we have done. And of course, I hope to share a little bit of those mistakes and my learnings with you. And to reiterate, I regret nothing. I learned a lot building this solution. Now, if you look back at that list, 3 weeks to POC, 3 months to build, 6 people and 1.5 years to fully complete, should you even build distributed systems? And I think the answer is, if you don't have to, just don't. You should try to not build a distributed system. And that might be a bit of a weird statement given the topic of this talk, but I really mean it. You shouldn't build distributed systems if you don't have to. Because they require a different skill and mindset than building monoliths or the type of applications that we're used to. So if you don't have that skill set or mindset in your team yet, it might be a painful experience to build a distributed system. Another thing, distributed systems are all about communication between different components, different applications, and that communication is complex. And what we know about complex situations is that they not only take a lot of time, but it's also very easy to get things wrong. And it's very hard to predict how a change will really work out in the real world. And of course, if there are more components, there are more costs. If you have a simple monolithic application running on a bunch of VMs or, I don't know, app services, that's always going to be more cheaper to run than multiple components distributed over different runtimes and different instances. And maybe leveraging some serverless or container components can get that cost down, but in general you can say that having 10 things running is always more expensive than having just one thing running. And finally, testing, monitoring and troubleshooting a distributed system is really, really hard. And that's again my personal learning. Now with that in the back of your mind, you might be wondering, then why are we building distributed systems? Or, to put it more clearly, why are we forced to build distributed systems? Well, there are a number of reasons, and I want to point out 4 of them. The first one is that if you have a distributed system, or many smaller components working together to deliver a grand total of functionality, you can limit the impact of errors. If you have a monolith and you have a mistake, it might be that the whole application blows up. If you have an out-of-memory exception or a stack overflow in one part of your application, it can consume all the resources and everything will go down. If you're running a distributed application and one component goes down, yes, you are losing functionality. But the majority of the application functions might continue to run. So next up, there is this focus for developers. If you have worked with big applications before, you know that they can grow and grow and grow and grow, and that the number of people involved grow as well. And what we know about software development is that it is primarily a communication problem. So as the number of developers in a team grows, or the number of teams that develop a single application grows, the overhead and the difficulty increases as well. If you have one smaller component and you align it with a single team, the team understands that component very, very well. And they can very easily and quickly make changes to that system. Now thirdly, there is the need for speed. Smaller systems change faster than larger systems. It's just a fact. The fewer lines of code, the easier it is to change. Smaller systems deploy faster. Maybe they have just one database instead of 5 different databases. They have one cache instead of 3 caches. The code base is smaller, the binaries are smaller, there are fewer tests to run. Smaller systems hit production faster. Smaller teams that come with smaller systems learn and develop faster. It's very easy to onboard a new team member in a small team that has a very, very focused scope. And finally, smaller components come and go faster. If you have a small component and its functionality is becoming obsolete, you just strike down the whole component and get rid of it. Just remember how hard it is to remove a little bit of functionality from a monolith that you don't need anymore. And the same goes with adding functionality, adding components or teams. Just set up the team, start building the component and connect it to the other components as soon as you are ready. And all of these contribute to the need for speed. And businesses need speed. Nowadays, I think the biggest competitive advantage for a lot of companies is the speed at which you can deliver software. So these are all kinds of pros, but there is also one thing that might really force you towards a distributed system. And that is because large organizations are complex. This is kind of the architecture that we developed in my team building a distributed system. Like I said, we had a transaction engine at the core. We had a bootstrap component that set up some base entities, base data. Then we had a user interface that the users could use to drive transactions. It was kind of a portalish thingy. In reality, it were HTML components that were hosted within another application. And then we had a series of transaction agents that executed all the transactions against the systems that they were managing. But if you look at who built this thing, after the proof of concept phase, we found out that the transaction engine and one of the transaction agents really belonged to my team. The bootstrap component, however, belonged to another team. Let's call them Team A. And they were very close by. They were part of the same department and we had a good relationship with them and we could walk over there if we needed them. Then we had the user interface. Now the binaries, the HTML for that interface, that was built by my team. However, the provisioning of those components in the grant application that they were running in was then again by team A. The system Y that we made our changes in, that we run our transactions against, was owned by another team, team B. And you should vision team B as kind of a platform team that manages an application, and our agent made changes on behalf of other users. Now team B was still very close by, but you can imagine that this relationship was a little bit harder because they were managing a platform, really in the ops role, and we were making changes, really in the change focused role. So there was a little bit of more friction here already. Then we had a team C, and they owned another transaction agent that worked against the system X that they already owned before joining this ecosystem. Now this team C was further away, still in the same department, but they had a different manager, a different product owner, and they were also offshored, by the way. And finally we had this team D. They already were running system Z for a while, and then they started building their own transaction agent to add support for managing that system Z through our transaction engine as well. Now this team was in a completely different part of the organization. They were physically not near us, they were organizational not near us, and we even disagreed on some points when it comes to a way of working, alignment of sprints, and those kind of things. And you can see here that while the system itself might not be very complicated, the layout of the organization really forced us to create different components that aligned with different teams. And this is often a driver for distributed applications. So now we know the difficulties of distributed applications, but you know why we built them anyway. Let's take a look at how we can test these things. So I think the first point to make is that you're going to need a proper pyramid of tests. Now this is not unique to distributed systems. This goes for any kind of system. But what's really important is that you do not do this. Don't have a few unit tests, many integration tests, a whole lot of system tests, and then manually test everything all the time. This is what we call an ice cone of tests, and this is wrong, in my opinion. I think you should do this, and this is what we call the testing pyramid. You have lots and lots of unit tests. You have fewer integration tests, even fewer system tests, and then only a few manual tests at the top if you really need them. Now for the sake of argumentation, my definition of a unit test is a class that tests the implementation of one other class. An integration test is a class that tests if one part of my system, often a class, can work well together with something outside of my system, a database, a queue, another system. System tests are tests that test a fully deployed system. And they often drive through HTTPS or through a test runner like, I don't know, Telerik. And finally, manually testing, yeah, well, that's what functional testers in the team do, or your developers. Now, the question that pops up once you've taken a look at this test pyramid is, how many tests do I need? Well, I think you should unit test everything you can. Unit tests are cheap to write, they are cheap to execute, they provide very fast feedback, and are a great way for fixating your requirements in an executable language, your programming language. Write integration tests against any other component that you have to integrate with to do two things. Verify your assumptions of what that system can do for you, and make sure that these tests and also the components that of the classes that implement them are as atomic as possible, and I will get back to that. System tests, I view them as a necessary evil. They are slow to write, slow to execute, provide slow feedback, but there are just things that you cannot cover with a unit test or an integration test. Prime examples being configuration in the dependency container. Now, the ratio between these things will differ from system to system, but I have found that the ratio of 1 to 5 or maybe 1 to 15 for every level of the pyramid works quite well. Now your mileage may vary, but This is just a general guideline. The point is, you should have much more unit tests than you have integration tests. Much more integration tests than you have system tests. You should only have a handful of systems tests, really. Now, unit tests, I think we all know them. Let's say that I have a requirement that the username should be of length 8, 9, 10, 11, or 16. Then I can create a test that verifies that any length lower or higher will be rejected whenever I try to create a new user. Write many of these types of tests. Now let's talk about integration tests. And here I have shown a few of the system that we're testing, and it can be seen that we, from class D, we call into another system through a RESTful API. This will require an integration test. Of course, classes A and C can be unit tested, so they are green, but for class D, we will use an integration test. Now, I think it's important to reiterate that the scope of that integration test should be as small as possible. Class D should only reflect the API capabilities of that RESTful API and not contain any business logic. For example, if that REST API has a call createUser, class D should have a method called createUser. And if I need any validations or retry logic or all kinds of other things, that should not be in class D. That should be in another class that uses class D for the execution. So class D only wraps the remote capabilities, and that means that we have an integration test scope that is as small as possible. Now, and then we can write an integration test that takes the same shape as a unit test. We instantiate our subject, we call the createUser functionality on the test class, and then on the same test class we try to find the user back, and we assert it is not null. This is a test that verifies that after we created the user, we can retrieve it back. And this class really verifies my interaction with the remote system and any assumptions that I have about the remote system. Now, one pointer here, and this is of course just an opinion, but I think we should really connect to the production environment of the other component. So if class D takes some credentials to connect to the remote system, try to connect to the production system, because the production system is definitely the most representative of how the production system is working. Their test environment, their acceptance environment might be slightly different. Now, of course, this is far from ideal if you have a system on the other side that cannot really isolate your workload. So even better would be if you could spin up a duplicate of their system only for your test and then spin it down directly after the test case. Maybe you can spin up their system in a container for a few seconds and tear it down after the test. Now, I think unit tests and integration tests will cover almost anything that you will want to test in your application, except for these nitty-gritty things that you can only find against the running system. Like I said, missing configuration, wrong credentials for an API, a mistake in the dependency injection configuration, those kind of things. For that, you will really need system tests. Now, if we take this picture of our system, it's in the middle, and our system, it defers some work through another part of the system via a queue. And our system is invoked by another system over HTTPS, and in the end we call another system over HTTPS again. How do you test such a thing? Now, what really worked well for us was that we first tried to identify flows that started in our system, or that came into our system, and where they left our system. So the first flow is the system calling us onto the queue, because the queue is a service that we buy from Microsoft. It is not a really an integral part of our system. And once we have identified such a flow, we can take out the other system, replace it with a call directly from our test. And that can drive the test and the scenario starting our system. And then, the end of the test should be that there is a message on the queue. And well, we can quite easily sense from our test if that message has arrived on the queue. So this is a very good scope for system tests. And that also means that if we now take a look at the other side, we think we can kind of do the same. We take out the other system that we should call, and we replace that with a send from the test. We see if a certain HTTPS call has been made. And to drive the test, we just put a message on the queue, and then we have a connected flow again. The problem here is that in my experience, it can be a pain in the backside to sense if the other system is called. Because if this is an outgoing call over HTTPS, of course you can redirect it to another endpoint, but then you should have an API running there that can take that call and register it as being made. And this can be done by stubbing out the external system. But writing a stub for a system is quite a lot of work. And whenever the other system changes, you have to change as well. So a shortcut that we took here quite often was in the running system for these kind of system tests. When we had to make an outgoing call, we injected a different class that didn't really make the outgoing call, but just registered the call as being made into a test context. Bit of a shortcut because it also detracts a little bit of value from the test, but it really worked for us. Alright, I think that concludes about 20 minutes of slides. So let's take a few minutes to see how these different things can be done when you're working on the Microsoft stack, the Microsoft cloud, like we are. Let's take a look. Alright, to show you some examples, I have quickly created a small application that can be used to demo the different things that I talked about. The starting point of this application is an ASP.NET application, a web API, that contains a to-dos controller. It's just a REST API that can be used for creating, deleting, getting or updating to-dos. This to-dos controller calls into a service that calls into a repository that is used for storing the to-dos. Next to this ASP.NET web API, there is also an Azure Function app. This contains one function that is triggered by any change in the CosmosDB database. Whenever there is a change in the CosmosDB database, the to-do is deserialized, and if it appears that that to-do is completed, the to-do is put on a queue. And that queue is consumed by another component that is outside the scope of this application. And that's what makes this a distributed application as a whole. Now, to take a look at how we are testing some of the things in this application, let's start with the simplest case, namely unit tests. Here I have the class that is used to represent to-dos. To-dos have a number of properties that are used for serialization, but instead of a regular constructor, I have chosen to add a static method for creating to-dos that also performs a series of validations. The name cannot be empty, the description cannot be empty, etc., etc. And if such a situation occurs, an exception is thrown. This kind of logic can be unit test to death. We do not need any type of test but unit tests for these kind of things. And unit tests allow us to write really simple quick tests like these. So I recommend you to write unit tests like these for any part of your system that does not integrate with the outside world. But for integrating with the outside world, there are that's more interesting, right? So let's take a look at my to-do repository. This is the class that is used for writing to-dos into CosmosDB. Basically, it is a small wrapper around the Cosmos SDK to provide an interface to my business logic that is easy to use for the customer of that API and allows me to put everything that is about interacting with CosmosDB into this single class. So this class gets a number of configuration options and uses that to instantiate the CosmosDB client that comes from the SDK. And that configuration basically is a locator of the CosmosDB database and the key to connect to the database. And then the class implements small wrapper operations around getting a to-do, getting all to-dos, adding a to-do, updating a to-do, or deleting a to-do. And there is one small private convenience method that can be allowed for getting a reference to the container that contains all the to-dos that we're interested in. And the name of the CosmosDB database and collection again come from configuration. So this class is definitely a good abstraction of my interaction with the outside world. And for that means that I cannot write unit tests for this class. Instead, I have to resort to integration tests. So here I have an integration test for this class. It's called to do repository test, and it takes the same shape as a unit test, but if we look closely, what I'm doing here is I'm instantiating what I call a Cosmos test context. This is another class that I've written myself, and this class is responsible for providing the configuration for connecting CosmosDB to the repository, and it is also responsible for creating a confined testing context before the test and cleaning up that context after the test. What we see here is that this context, when it is instantiated, it gets a CosmosDB endpoint and key from the test context and also a database name. But instead of getting a collection name from the test context, it generates one on the fly. That means that when we set up our test context, I am actually creating that container specifically for this one test. And that means that when I am done with the test and I want to tear the environment down, this container is also removed. And I added a convenience method to return a CosmosDB configuration based off the settings that are both passed to the test context and generated in the test context. So using this test context, I can now create an integration class, integration test class, that tests my to-do repository using that context. And as I create that context and tear it down, for every individual test, I am testing the most minimal atomic part of code possible, making sure that my integration tests are small and relatively quick and can be really used to verify my assumptions about how the external system, CosmosDB in this case, works. And I can use this principle in many, many more contexts as well. I have another class called queueMessageSender, and this is the class that I use to send messages to the queue whenever I need to. And here we see that I do the same thing. The class is a small wrapper around an SDK component called queueClient, and that component is instantiated in the constructor based on some outside configuration. And then the send message is just a convenience wrapper around the SDK method, wrapping both serialization and sending the message. And to test this class, I again have to refer to an integration test. I do the same thing. I have created my queue test context. I set it up. Then I can create a queueMessageSender and I can execute my test. Now this test is a little bit larger because what it does, it creates the to-do to put on the queue, and here I actually send the message to the queue, but now I'm using the SDK capabilities to also listen to the queue that is created specifically for this test context. And then after sending the message, I'm going to wait as long as there is no message received by the test. And I hope that these two examples show how I've isolated a most minimal dependency on an outside system, and I'm very, very specifically testing only that integration with the outside point, minimizing the scope for my integration test as much as possible. Now the final thing that I want to show is the system test. Here we take not a small atomic part of the system that we want to test, but here we want to test the full user flow to the database. And as you can already see from the body of this test, these kinds of tests are more work to write and they have a larger test scope. But what this test does, it creates the to-do and then it really calls into the running system to post that to-do. It waits for that API call to succeed, and what it then does, it then connects directly to the database using a Cosmos client, and it connects to the collection that is used by the test deployment of the system, and it verifies if it can find the added to-do in the database. So this test really verifies that an end-to-end flow is running from a user calling the system all the way to the data being stored in the database. And these three types of tests layered upon each other I believe provide a very good foundation for testing a component completely in isolation using fast feedback principles. Now the final thing to know here is where all these parameters and settings for the test context come from. They come from a specific file called the run settings file, and I provide them to my test runner. And here you can see the file as it is checked into source control. It contains the different settings, but instead of the actual value, I am providing a placeholder. And in my deployment pipeline, I replace the value for that parameter with the actual value that comes out of the infrastructure deployment. So in my pipeline, I first deploy my infrastructure and then the returned values I use during my tests. And all of this combined means that I can do things like this in my deployment pipeline. In the first stage of my pipeline, I not only built my infrastructure definition, which is an ARM template in this case, but I also built and packaged all the different types of tests that I want to execute from within my pipeline. Here you can see that I compile my sources and that I then run my unit tests. And after running the unit tests, I also publish, of course, the binaries so that I can later on deploy them to my test environment. But I also publish and package all the different DLLs that contain my tests. And that means that after I've deployed to my test environment, which I do right here, I deploy the ARM template, and then I fetch the outcomes so that I can deploy my binaries. But once that is done, I start running my integration tests. These execute the tests that we have just seen before. And one of the things that I do, and that's interesting to see, is that I replace the values for that run settings file with the values that come out of the actual deployment. So now my integration tests are running against the infrastructure that is just deployed into Azure. And once all my integration tests have completed as well, I proceed to my system tests to do the same thing. Now, of course, this demo might have been a bit fast, but not to worry, all the code and all the examples and also the full definition of the pipeline can be found on my GitHub account, github.com/henrywayne, within a couple of days. Alright, now that you've seen how you can do such a thing in Visual Studio, let's move on with some slides again. I hope I have convinced you that testing distributed systems is hard, using automated tests. But there is one type of test that is even more difficult, and that's the manual test. Because if you get into manually testing distributed systems, there will always be someone that makes a claim like this. It is our job to verify that our system integrates correctly with all the systems that call into us and all the systems that we call into. It can be a tester, it can be a business analyst, or a risk-averse product owner. Somebody will insist upon a connected systems test. Now, the thing is, they are kind of proposing that you connect your test environment to the test environment of another team. And then they make a change in the system of the other team and they check if your system is called correctly and it behaves as it should. And the question is this a good idea? Now, I'm slightly opinionated on this point. No, I don't think so. And let me explain why. So first of all, they will not stop before all the test systems are connected. Because A needs B to start, and B needs C to run, and C needs D to complete, and D needs E, and before you know it, there will be tens or hundreds of smaller test components connected all throughout your organization. And the problem of that is that once your test environment is down, others cannot test because they are depending on tested environments. So you will start getting complaints when your test environment is done. Now, for your production environment, you might be willing to accept that you get complaints when it is down. But do you really want to take complaints when your test environment is down? And another thing is, all the tests that run against all these environments, do they really provide value? If you think about it, all these test systems, they have internal state, internal databases. But these databases are not really in sync. Because a team over there does some testing, leaves some inconsistent state in their database. Another test environment was down for 2 days, so they made some of the changes in an upstream system. tests that run against these kind of data stores are not really representative for what will happen in the real world. So the value from these kind of tests, I believe, is quite limited. So then somebody comes up and suggests, why don't we connect all the acceptance environments? The question is, should we do that? And again, I'm slightly opinionated on this subject. I don't think that that's a really good idea. Let me try to explain why. First of all, they will still not stop before all the acceptance environments are connected. Now you might be a little bit more open to accepting complaints where your acceptance environment is not running, because it's a way towards production, but still it is annoying because your responsibility is to production and not to non-production environments. But there is a much bigger problem. Besides the problems that still persist here, because the state between systems is probably not consistent. But there is another problem as well. Taking a look at the picture, we see that our current acceptance environment is running version 4.86 of our software and is tested against their acceptance environment running 0.32. And let's assume everything works like a charm. It works perfectly. And we want to go to production with our environment. So we're going to make this change and we're going to update production to 4.86. There is a good chance that everything will stop working. Why? Well, because we verified that our 4.86 works with their 0.32, but we have no clue if it works with their 0.30. Their acceptance environment is the next version they want to take to production. It is not necessarily the version that they are running in production. Now the answer here from a lot of people is that they put in place release trains. So first they go to production and then a day later we can go to production, or maybe we all go to production at the same time. But then you're kind of back in the Big Bang scenario, in the monolith scenario. If we all go to production on Tuesday morning, one after the other, we don't have limited impact, we still have to coordinate between all services, we don't get the benefits of a distributed system. So I don't think that this is a good idea either. Like I said, you will only know if your software works with future versions of dependencies, not of the current version. Now your question is then, how do we execute representative tests? Well, east-west, production best. There is no place to verify that your stuff is really working than the production environment. And I will show a number of examples on how you can do it safely. Because let's be honest, this will be faced with a lot of resistance by people in your organization. So the first thing I think that we already know, for a lot of people know and are using about testing in production, is the use of feature toggles. Feature toggles allow us to take two implementations of the same functionality and then enable the one or the other based upon configuration. So we deploy our system and the old code, now behind the toggle, keeps running, and at some point we switch over to the new implementation. And if there are errors that show up, we switch back to the old implementation. This is a great approach. But there is another step, and that's what we call experiments or experimentation. We take this idea of having two implementations side by side, the current one and the new one, but instead of running the one or the other, we're going to run them both. And we're always going to return the result from the current implementation, but we're also going to check if the new implementation works better or at least just as good as the current implementation. Now this is a subject of its own, and I have written an example on my blog, you can find the link at the bottom, that runs two implementations of calculating the nth number of the Fibonacci range. And this C# code in essence shows how to run experiments in production. Basically you duplicate your code, change one of the copies, and then execute both paths in parallel in your code base. And then you always return a result from the old implementation, but you're going to check if the two results are the same. And if they are not, you're going to log that to your systems. Now what you see here is the code that is used when you use a package called Scientist, and it's a NuGet package that you can download from nuget.org and has built-in support for running these kinds of experiments. And I think this is a great example of how you cannot shy away from production, but really verify if your code is working correctly in production. But this is about, changes that you make to your code. Talking about distributed systems, one thing that's really important is testing if my stuff still works correctly with the stuff of another. And a technique that we can use here is called contract testing. When you are using contract testing, both the producer and the consumer of messages, it can be messages on the queue, and that can be stuff in the database, it can be HTTP calls back and forth, you both constantly validate that all the messages sent or received conform to agreed contracts. And if not, you just decline the message. And you do this especially in production. So for example, you agree upon a JSON schema for a message on the queue. Now what you do is, I have a queue abstraction that I can use to write messages to the queue. And as we stated before, when it comes to integration tests, this is a very minimal implementation. An implementation that only wraps an SDK object for sending a message to the queue. Only so that I can test it in isolation and mock it out in the remainder of my tests. But I'm going to add one small thing. Instead of having only a dependency on an object of the SDK, I'm also going to take a dependency on a message contract validator. A small class that will validate every message in production before it is submitted to the queue to see if it is valid and adheres to the contract. And the consumer of the messages, in this case a function that reads messages from the queue, is going to do precisely the same thing, in opposite. I have a function that is triggered by a message on the queue, and before it starts up my business logic to process the message, it is also calling that message validator to validate if the message is valid. Now of course both validations have to use the same schema, so often you will see that the consumer of the messages will publish a description of the messages that it will accept. So this is contract testing, and I think this is a very, very powerful technique to verify if your code can still work together with the code of another, if you can still interact and communicate correctly. So this is kind of what I wanted to share about testing distributed systems. Let's now swap over to how to monitor distributed systems. And I think the first bit of advice is going to be not new if you're already monitoring a monolith. For example, make sure that you alert on every backend invocation failure. A lot of distributed systems will have a front end that accepts messages, puts them on the queue or in a database, and then a backend that processes these messages. And the front end is responsible for making sure that it validates if the message is valid and it can be guaranteed to be processed before it moves to the asynchronous process. Now, if there are any errors in the backend, there is often no way for reporting back to the user. So I recommend that you treat every invocation failure as an alert and that you follow up manually to see what has happened and to prevent it from happening again. For all your messaging, have dead letter queues. Whenever you cannot process a message and you have tried for 3 times, do not just dump the message on the ground, but move it to a dead letter queue so that you can inspect it later and find out why it didn't work out. Alert whenever a new dead letter message occurs. And make sure that number 1 and number 3 are mutually exclusive so you don't get 2 alerts for the same problem. Make sure you put alerts on all your resource consumption limits. When you move to distributed systems, you're often going to be very confined in the capacity that you can use to control that cost that often comes with distributed systems. So make sure that when your database consumption reaches its limit, or when you're reaching the limit on the number of messages that you can put or retrieve from a queue per second, make sure that you get alerted so that you can intervene and scale up. Make sure that you talk about how to go about logging with your team. In my team, we agreed that we are going to use all the log levels available, trace, debug, informational, warning, error, and critical from our systems to kind of indicate how important the log entry is, but we left it open to every individual developer to make the decision, except for critical log entries. There we made a very strong statement saying that if and only if a log needed manual follow-up by a developer or somebody else in the team, you should emit a critical log entry. And after that, we put in an alert that whenever a critical log entry was emitted, the team would be alerted to it. And we would follow it up and we would investigate it. Now all of this only works when you also agree with the team that you will fix all the causes for alerts as soon as they come in, or remove the alert altogether if it just generates noise. If you only do this and don't do this, it will take less than a week before everybody will start ignoring the alerts. So this doesn't really differ from how you would monitor a monolith. Maybe it's a bit more rigorous, but that's it. For distributed systems, there are two more things that I would recommend. And the first one is distributed tracing. Distributed tracing is a way for making sure that whenever a first component is invoked, and that component invokes a second component, and that invokes a third component, there is a correlation ID that traffics along with that flow. And that all the logs being made in the different systems are all related to that correlation ID. That way, if something goes wrong somewhere in the system, from that log entry, you find the correlation ID, and then you find all the information throughout all components relating to that correlation ID. And that way you can follow the invocation through all your different components and maybe investigate better or troubleshoot quicker what has gone wrong, or identify wrong assumptions between components. If you have a distributed system but no distributed tracing, troubleshooting will become very, very hard. And the second tip is use synthetic user monitoring or use case monitoring. Have another system next to your main system that executes 1 or 3 user flows against your system every 10 minutes and validates that they are working correctly. You can have all the unit tests, integration tests, system tests in place, but they are all focused on finding mistakes. This synthetic monitoring does the opposite. It constantly verifies that everything that should be working is working. And I thought I'd give you a quick demo of how we do that second part in our application. Now there are many tools out there for implementing synthetic user monitoring. But if you want to start small, or if you just want to give this thing a try, I want to call your attention to this very simple, straightforward method that works as well. What we do, we just create an Azure function plan where we implement in the shape of an Azure function a synthetic user flow. So this is a function that is designed to run once every 5 minutes, and also on startup of the application. That runs through a user scenario for creating a to-do and then marking that to-do as completed so that it is sent over the queue to an external component. And then it starts waiting till that to-do is billed to the customer. Because apparently after we've sent that to-do away on the queue, there are other components involved with calculating the pricing and sending an invoice to the user and then registering it in our system containing all the bills. So here I have written a bit of simple code that runs this scenario through my system after deployment every 5 minutes. And actually the code that runs this is part of my system. If this is running in your real environment, you might probably move it to a separate function plan. But this is what I mean by synthetic user traffic. We put load, synthetic load for our application that verifies that it's working correctly in our production environment right next to our application. And once you do such a thing, this is the result that you can get for running that function. So as soon as my application starts up, now every 5 minutes, the implementation of not only my component, but all other components that I interact with is verified in the actual environment. And of course I can attach an alert to the failure of this function so that I will get notified as soon as there is no working application more. Alright, let's go back to the slides for some final takeaways. So I think the first big takeaway is only build distributed systems when you really have to. If you can prevent it, don't do it. Alright, that being said, a number of recommendations. do not connect your non-production environments with other components' non-production environments. It will be a never-ending story and it will take a lot of time, and it doesn't really deliver value in my opinion. Build a proper pyramid of tests for your system. Everything you can test in isolation, you should test in isolation. Now also provide a good means for integration testing to your consumers. I didn't cover how to do it, but the recommendation is fairly simple. If you have a component and others will use that component in production, also give them access to your production environment for their integration tests and for their acceptance tests. Now there might be some objections to this from, testers, but what if they break our system in production? Well, they shouldn't be able to break your system in production because it's your production environment. And there is no environment where you can give bigger guarantees about it being production-like than production. And if by incident one of those teams breaks your production environment, don't keep them away, but instead improve your production environment and harden it. So open up your production environment to everybody that wants access to it. Consider contract testing. It can be a bit of work, but it really delivers value because you constantly, at every call back and forth, validate that you are still adhering to the agreed way of communicating between components. Make sure that you rigorously monitor every component at the individual level. But since this is very system oriented, make sure that you also have your synthetic user scenarios monitored. And finally, if something goes wrong, implement distributed tracing so that you can see what has gone wrong, why it has gone wrong, who are impacted, and how you can prevent it from happening again. Alright, with all that, let's wrap it up. I do really want to recommend you to try this at home. I do hope you enjoyed the talk. If there are any questions, feel free to reach out to me, or you can ask the questions right now in the chat because I'm there as well. Thank you and have a great conference.